All right, welcome back. This is 6.1. So we are officially done with the linear algebra part of this class, and we're going back to Nagle's differential equation. We're looking at starting with 6.1 basic theory for a linear differential equation. So in this section, we will try to combine both what we learned from in the beginning differential equations along with some linear algebra ideas, especially linear independence and linear dependence. So notes are available again on Blackboard. Let's take a look at the first thing, differential operator, L. That is defined, right? So we will use a colon and then equal means defined as dny, dxn, and so on. Right, something like this. Right, so the L is just some linear operator, which is just a symbol that tells us that we're going to take derivatives of y's in many different ways, so that the nth derivative and then n minus 1 and down to the original function y. And all the pi's, the p1, p2 up to pn, they're just some of the functions in terms of x. And on the right-hand side, this is just another way to represent the linear operator. Now, this is just some introduction to the symbol that we will see later, but we're not going to focus too much on this symbol of L, but just remember that L means a differential operator. All right, so next, let's look at definition 1, which is the Wronskian. All right, so the Wronskian here, let's look at the definition together. Let f1 to fn be any n functions that are n minus 1 times differentiable. N minus 1 times differentiable means you can take all of these functions and derive it up to n minus 1 times. Now, of course, some of them may be infinite times differentiable, but we want them to be at least n minus 1 times differentiable. All right, so the function w, right, capital W means the Wronskian of these functions is defined as this, right? So let's look at this matrix together. The first row, you just have the functions f1, f2, up to fn. And then the second row is going to be the first derivative of all those functions in the first row. And then, of course, the second row, the next row will be double derivative and up to the nth row, which is n minus 1 times derivative of all these functions. Right, and this is called the Wronskian of f1 to fn. Now notice that they are a little different, right? Instead of using the square bracket to represent matrix, we are using bars. Now, do you guys remember what bars means? Right? Yes, so bars means we're actually looking at the determinant of this matrix right here, right? So once you have all these functions listed out, we are going to take the determinant of it, and the determinant is called the Wronskian of f1 up to fn, right? So Wronskian means the determinant of this matrix. So this is going to be a determinant. Of course, with so many functions, it might take us a lot of time to find the determinant. But later on, we'll see some easier examples. And we will look at what does the Wronskian tell us about these functions. Now let's move on to theorem 2. Theorem 2. All right, theorem 2 says it gives us the representation of solutions to the homogeneous case, right? So we're more pretty similar to what we saw in the beginning of the class, right? So let y1 up to yn be n solutions on A and B for this differential equation right here. And as you can see that it's a very high order differential equation where P1 up to Pn are continuous on the domain A and B. If at some point x0 in A and B, the solution satisfies the Wronskian of all the y1s not equal to 0, right? This is the crucial part, not equal to 0. Then every solution of this equation, 17, on A and B can be expressed in the form of y1 is equal to the linear combination of y1 up to yn with the constant c1 up to cn, right? So this is something very similar to our in the beginning we look at second order for first order linear differential equation, right? We're just bringing up to a higher order, so we have similar form of the solution, right? So the linear combination y1 to yn in equation 19 is referred to as the general solution to this differential equation. Now, keep in mind that we are only working with the homogeneous case, which means the right-hand side of the differential equation is 0. Okay, remember the homogeneous case. And later on, we will look at the case of non-homogeneous, meaning when we have a non-zero term on the right, or some non-zero terms on the right. All right, so scroll down a little bit to look at definition 2, linear dependence of the function. Let's look at the definition. Now, this linear dependence and independence, they are very similar to what we talked about in linear algebra. Right, so let's look at the definition together. Definition 2, the n functions f1 to fm are said to be linearly dependent on an interval I if at least one of them can be expressed as a linear combination of the others on the interval I. Equivalently, they are linearly dependent if there exists constant c1 up to cn, not all 0, such that this equation is equal to 0 for all x and I. Otherwise, they are said to be linearly independent on I. So let's take a few minutes and try to review what we're talking about here in terms of linearly independent and linearly dependent. Okay, so example 1, we have 3 functions, e to the x, e to the negative 2x, and the third function is 3e to the x minus 2e to the negative 2x. And we want to show that these 3 functions are linearly dependent on all real numbers. Okay, so to check linearly independent or linearly dependent, what we're looking at is this equation, right? C1 F1 plus C2 F2 plus C3 F3 is equal to 0. All right, so let's break it down into cases. If the only solution is C1, C2, C3 all being 0, then this is, then we say that they are linearly independent. Okay. That being said, if we can find a solution, a set of solutions C1, C2, and C3 such that they are non-zero, one of them is not 0, then we can say that this equation right here, or these 3 functions f1, f2, and f3 are linearly dependent. Right? So example 1 says we want to show that this is linearly dependent. All right, so let's look at these 3 functions. We have c1 e to the x plus c2 e to the negative 2x plus c3 3e to the x minus 2e to the negative 2x is equal to 0. All right, so let's see. Are there any ways to pick C1, C2, and C3 such that they are non-zero? Let's check. All right, so let's expand the left-hand side, C1 e to the x plus C2 e to the negative 2x plus 3C3 e to the x minus 2c3 e to the negative 2x is equal to 0. All right, let's combine some of the like terms. All right, so we have e to the x, c1 plus 3c3 plus e to the negative 2x, c2 minus 2c3 is equal to 0. All right, so this is very interesting, right? If another way, if we can make them 0, then we're done, right? So let's say let C3 be 1, right? Then in order to make this a 0, I get a plus 3 here. That means I can pick C1 to be negative 3, And if C3 is 1, then I can pick C2 to be a 2, right? So when C1 is equal to -3, C2 is 2, and C3 is 1, these three numbers, notice that they are non-zero, satisfies this equation right here. Right? That means we actually have non-zero solutions to this equation, right? That means they are linearly dependent. Okay. Keep in mind that the definition is we want the only solution to be all zeros, so they will be linearly independent, right? If we can find some non-zero combination of the C1, C2, and C3s, then we can say that they are linearly dependent. Okay. Of course, as we have more functions, it's going to be a little more annoying to, or a little more time consuming to check if they are linearly dependent or independent. And this is why we have our next theorem, theorem 3, which is going to help us a lot by checking if a set of functions we have are is linearly dependent or linearly independent. All right, so let's take a look at theorem 3 together. Okay, so let's take a look at this together first, and then I'll talk about what they are. So theorem 3, linear dependence and the Wronskian. If you have n functions, right, y1 to yn, and they are solutions to some differential equation, homogeneous, with p1 up to pn continuous on AB, then the following statements are equivalent. Okay, so the first three, let's look at the first one. Y1 to Yn, they are linearly dependent on A and B. Now, of course, a lot of the times we need to check that, but this is when the next two items will help us tremendously on determining whether Y1 up to Yn are linearly dependent or not. Okay. Second, the Wronskian is 0 at some point x0 in A and B. Okay. So if we can show that the Wronskian, the determinant of the matrix that we saw earlier, is 0 at some point A and B, then we can say that that's linearly dependent. Or the Wronskian is identically 0 on A and B. So in both cases, if you can show that the determinant of the matrix that we saw earlier is 0 at some point in the domain, or is always equal to 0, then we can say that they are linearly dependent. Okay. On the other hand, let's look at the bottom three. On the contrapositives of these statements are also equivalent. These functions, y1 up to yn, are linearly independent on A and B. Right? So that's the first statement. And the next two is the Wronskian is non-zero at some point x0 in AB. Right? So if you can find a value such that the determinant of this matrix is non-zero at some point AB, then we can say that it's linearly dependent. Or if we can show that the Wronskian is never 0, then that also means we can say that the set of function is linearly independent. Okay? Whenever 4, 5, or 6, which are these 5s, is met, this set of function is called the fundamental solution set for 17 on AB. So 17 is the equation from earlier, which is this homogeneous case differential equation, higher order. Okay. Next, we're going to use this idea, theorem 3, to check if of the function, we have another set of 3 functions, and want to show that they are actually linearly independent on the interval -infinity to +infinity. Okay, so there are actually many ways we can show that F1 to F3, they are linearly independent. There is a method in the textbook, you can read that, or in here, I actually want to show you how to apply theorem 3. Meaning, if we can show that the Wronskian is non-zero at some point, then we can say that these 3 functions are linearly independent. Okay? So let's set up the Wronskian first. Let's do a quick review on the Wronskian. Right, so we just have three functions, right? First row is just the original three functions. Second row, we're going to look at the first derivative, right? And then the last row, since we have three functions, we only need three rows. And then that will be f1 double prime, f2 double prime, and f3 double prime. Okay, so all we need to do is just fill in all these functions and find their determinant. Right? So let's do that. F1 is x squared, 1 minus 2x squared, 1, 2x, negative 4x, and then that's 0, 2, and negative 4. All right, so if you look at each column, to go to the next row in each column, you just take the derivative, right? Derivative of x is 1, and then again 0, x squared, derivative 2x, derivative 2, and then so on. Okay. All right, now that we have this set up, let's just find the determinant together. And I'm going to use, since this is a 3 by 3, I'm just going to use my method, right, adding the extra columns on the right. And then you go down, multiply, and then go up, multiply, right? Okay. All right, let's do the downwards one first. All right, so x, 2x, negative 4, negative 8x squared, and then you hit a 0, so that's just a plus 0. All right, so plus, that will be a 2 minus 4x squared. All right, and then now next, let's go from bottom up. And to go from bottom up, we're subtracting. All right, so subtracting, that will be minus 0. All right, and then minus negative 8x, so plus 8x squared. And then minus negative 4x squared, so plus 4x squared. All right, so a lot of the stuff are going to cancel out, right? The negative x squared and the positive 4x squared, leaving you just a 2. Okay, so 2 is never 0 on negative infinity to positive infinity. Right? So let's look at the theorem again. All right, so theorem 3, they are linearly independent when Wronskian is non-zero at some point in B, or Wronskian is never 0 on MB. Right? So for example 2, we show that the Wronskian is a constant 2, which means it's never going to be 0 on negative infinity to positive infinity. Right? So we have shown that 0.6 is true. That means 0.4 is going to be true as well, meaning they are linearly independent on the entire domain, negative infinity to positive infinity. All right, so we can say that this is never 0. Therefore, F1, F2, and F3 are linearly independent. Okay, pretty nice, right? We have a really rigorous method on checking if three functions, or we can have more functions, are linearly independent or not. All right, next we're going to do a quick review on a non-homogeneous. Right, so non-homogeneous differential equation means you have something on the right hand side, right? It's not just so yn plus p1 y minus 1 plus dot 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 plus pn y is equal to some function g of x, right? So now we have something on the right hand side. It's not going to be homogeneous, right? Remember, the homogeneous case is when the right hand side is a 0. Okay, now back into second order, right? We know that the general solution has two parts. It consists of the particular solution with the general solution for the homogeneous case, right? We have two parts, right? The particular solution, which is based on g of x, and the homogeneous part. Oh, the homogeneous part. Okay, and same thing here with the higher order differential equation. We still have this form of solution which is constructed by combining the particular solution with the homogeneous solution. All right, so let's take a look at theorem 4 together. All right, so theorem 4, that y sub p be a particular solution to the non-homogeneous equation right here on the interval AB with P1 up to Pn continuous on A and B, and that Y1 up to Yn be a fundamental solution set for the corresponding homogeneous solution, right? So the Y1 up to Yn, they are going to be part of Y sub H. Then for every solution of equation 27, the non-homogeneous case, this can be expressed in the form of y of x is equal to y sub p, which is the particular solution, plus the solution from the homogeneous part, right? So the C1y1 up to Cn yn, when you add them all together, they give you the homogeneous solution. And we just add that to the particular solution, and we will get the solution to the non-homogeneous case, right? So next, we're going to look at example 3 together. Now, in this section, since we're looking at higher order, it's a little more confusing, a little more challenging to solve for the particular solutions and the homogeneous solution. Right? So in this section, a lot of the times they will be given to us, the particular solutions and the homogeneous solution. Right? So let's solve them together. All right, so first we see the linear operator symbol on y, meaning we're defining the differential operator on y as this differential expression right here, y triple prime minus 2y double prime minus y prime plus 2y, and that's equal to this expression right here. All right, so in general, this whole thing is just our differential equation, right? Okay, and we can clearly see that the right-hand side of this differential equation is non-zero, right? Meaning we are actually looking at a non-homogeneous case, right? So we have to find first the particular solution and then the homogeneous part of the solution to the homogeneous part. Okay, and the question also gives us the solutions, the particular solutions, and the solutions to the homogeneous part, which are these. All right, so x squared and e to the 2x, e to the negative 2x, they are particular solution. And to be a little more specific, the first one, x squared, is the particular solution to the first three terms, 2x squared minus 2x minus 4. And then the second particular solution is for the last term, which is negative 24 e to the 2x. All right, now remember, for particular solution, we also need to do something is solve for the coefficient. Remember the method of undetermined coefficient, right? So that's what we have to do now, is to find what value goes in front of the particular solution. Now, of course, for the homogeneous part, we will have C1, C2, and C3 because we will need initial values to find out what all the C1 up to C3s are. But for particular solution, we can find out what they are just by plugging them into the equation. Okay, so let's do that now. Okay, notice that I'm only looking at the first particular solution and then corresponding to the first three terms on the right-hand side of the equation, right? Because we know that the fourth term, the minus 24e to the negative 2x, this term corresponds to the second particular solution. So we can take care of that separately, and we will see that later. Right, so first, we can just focus on the first particular solution, which we know is from the first three terms. Right, so go ahead and find out all the derivatives, and then we will plug everything in. Now, finding a derivative should be pretty easy, so I'm going to give you guys a second. If you want to pause, you can. All right, so here we have it. Y prime is 2ax, y double prime is 2a, and y triple prime is 0. All right, so let's plug everything into this equation and try to solve for a. All right, so we have y triple prime 0 minus 2 times y double prime, which is 2a, so minus 4a, minus y prime, minus 2ax, plus 2y, so plus 2ax squared is equal to 2x squared minus 2x minus 4. All right, so let's look at, put everything together. All right, so we have 2x squared minus 2ax squared minus 2x plus 2ax minus 4 plus 4a. I don't know if you can see what a is going to be already, right? So 2x squared is 1 minus a, minus 2x, 1 minus a, minus 4, and 1 minus a, right? And that's equal to 0, right? So the only way to make everything 0 is when 1 minus a's are 0, right? And that's very nice. It tells us that a is equal to 1, right? So our particular solution, or y1, for this differential equation is just 1 times x squared, which is x squared, okay? Which is very nice. All right, now let's look at the second one. All right, so second particular solution is e to the negative 2x, and again we want to find out what the coefficient is for this differential equation. Now again, if you look at the right hand side, we are only looking at the last term, the negative 24 e to the negative 2x, because we took care of the first three terms in the previous part, which is when we were looking at the first particular solution. All right, so do the same thing. We want to take this function and plug in to the differential equation right here, and again take some time to find out what the derivative of yp2 is. All right, here we go. So we have them right here. It's not as easy as the previous one, but it's not going to be too bad. All right, let's go ahead and plug everything into here. Let's see what we have. So y triple prime, negative 8 b e to the negative 2x minus 2y prime, y double prime. All right, so minus 8 b e to the negative 2x minus y prime, so that'll be a plus 2 b e to the negative 2x plus 2y, so plus 2 b e to the negative 2x, and that's equal to negative 24 e to the negative 2x. All right, so notice that the left hand side, they are all like terms, right? So we can combine them. Negative ab, negative 16b plus 4b, so that will give me negative 12b e to the negative 2x is equal to negative 24 e to the negative 2x. All right, so by solving for b, we get that negative 12b is negative 24, so b is 2. All right, then we can say that our second particular solution is going to be 2 times e to the negative 2x, like this. Okay, so we have both particular solutions ready, and we have 3 homogeneous solutions, and we can combine all of them together to get our general solution. Okay, so from based on our work, we know that the 2 particular solution looks like this, right? And the homogeneous solution are given to us are these, right? Now let's actually look at the homogeneous part together. We have e to the negative x, e to the x, and e to the negative 2x. And something important to notice here is that these 3 are actually linearly independent. Right? Linearly independent means you cannot obtain one of them from a linear combination of the other 2. Right? This is particularly important when we are looking at homogeneous solution. If one of them can be obtained from the other 2, then your homogeneous solution doesn't have to contain the third one, right? Because you can get the third one from the other two, right? So it's important to check that the set of homogeneous solution functions are linearly independent. And then let's go ahead and write out our general solution, y of x. That y is weird. Y of x is first the particular solutions, x squared plus 2e to the negative 2x, right? That's the particular solution. And then plus the homogeneous solution. Now remember, for homogeneous solution, we need to add c1 e to the negative x plus c2 e to the x plus c3 e to the 2x. Okay, and that's it. That's how you write out the general solution for a non-homogeneous case. The particular part, right? The yp's and the yh's, right? From the homogeneous part. Now, again, since no information is given on the initial value, right? So there's no way we can find C1, C2, and C3. So to find those, we need initial value. Right? Now, if the question does give you an initial value, then you'll be able to find C1, C2, and C3. Okay? Now remember that since we have 3, we will need 3 equations, 3 initial value. All right, so that basically wraps up 6.1. Now, this is just like a really quick look into higher order differential equation. In this class, we're actually not going to too much methods on solving a higher order differential equation. But in this case, we can see that it has many resonance to linear second order and or linear first order. We have a lot of the similar ideas, right? For example, the general solution is made up of the particular part and the homogeneous part. And of course, one big thing is knowing how to use the Wronskian to check for linearly independence or linearly dependence, which is a really big part of the section of Theorem 3. All right, so thank you guys very much, and feel free to come up to office hour Tuesday, Thursday, 1 to 3 p.m. The link is available on Blackboard. And have a good day. Stay safe and stay healthy.